the second talk of this session, and we'll have Clémence Chevignard from INRIA, who will tell us about reducing the number of qubits in quantum factoring. So let's welcome Clémence.
Thank you very much for the introduction. Sorry for the delay for the installation. Today I'm going to present to you a memory optimization of a quantum algorithm, Shor's algorithm specifically, that allows, among other things, to factor integers. Please note that this is a joint work with Pierre-Alain Fouque and André Schrottenloher. Before detailing how our reduction works, I'm going to talk a little bit about the algorithm we target, which is Shor's algorithm. So, the remote isn't working. No problem. So, as I just mentioned, Shor's algorithm allows to factor integers. From now on, we are going to assume that we specifically want to factor integers big N that are a product of two distinct primes, P and Q. To do that, the general idea is you will choose at random an integer A in Z over NZ. You will try to find the multiplicative order of A in Z over NZ, which means concretely that you are looking for the smallest positive integer x such that A to the power of x modulo big N is equal to 1. And once you've done that, if x has the right properties, you're able to deduce the prime factor of the integer n we want to factor. And if x doesn't have the right properties, you just change the value of a and you redo all of the steps over again until you find something suitable. The part where we need a quantum computer to run this algorithm is the second step. So in order to find the multiplicative order of a modulo big N, what we do is we take a register S and we are going to put into this register an equidistributed superposition of every pure state representing the pairs xi, a to the power of xi modulo big N, with x that goes from 1 to an integer that is of the order of magnitude of big N. Since we are representing pairs in our register in any case, we are going to consider that the input part of the register S contains the xi and the output part of the register contains the a to the power of xi, modulo big N. Once we've set up our register S, what we do is we are going to apply a quantum Fourier transform on the input register. So for those that don't know the formula by heart, this is what this kind of transformation do. And once we've done that, we apply a measure on the input register once again, and we are able to deduce the multiplicative order of A modulo big N from that. If this is your first time seeing Shor's algorithm, maybe it's a bit unclear how things work at this point and why we use the Fourier transform at this point. Roughly speaking, one of the things the Fourier transform allows to do is it allows to exhibit the periodicity in a sequence of number, okay? Here, we're interested in the smallest positive x such that a to the power of x modulo big N is equal to 1. So if you consider the sequence of number of a to the power of x modulo big N with x that goes from 1 to the infinity, this sequence is periodic and the period is precisely the multiplicative order we are trying to find. And you can notice additionally that there is a small part of this number sequence that appears in the output register of our register S. So basically, using the Fourier transform allows to observe the period of this chunk of number sequence. That's why this algorithm works. Since we have to store integer modulo big N on our register, we have a qubit complexity for Shor's algorithm that is linear in the bit size of the integer big N we want to factor. Let's name N this bit size. In cryptography specifically, one of the main reasons why we are interested in this algorithm is because it allows to break the RSA crypto system, which is a very well-known and very widely used crypto system nowadays. Concretely, a part of the private key of the RSA crypto system is a number that is a product of two distinct prime numbers. If you are able to factor it, you completely break the system. The problem that we have is that in current use of I mean, with the use we do of the RSA crypto system nowadays, we have an integer big N to factor that is usually 2048 bit long to 4096 bit long. And of course, we don't have quantum computers big enough to factor that kind of integer nowadays. So there has been some previous attempts to optimize the memory of Shor's algorithm. The previous best prior to our work was due to Zelka and achieved a qubit count to run Shor's algorithm of 1.5 times n plus a negligible amount of qubits. What we do is we take this number down to n over 2 plus a negligible amount of qubits to factor big N. To achieve this result, the first thing we do is we integrate our memory optimization to a previous existing one that is due to Ekera and Hastad, and that allows to shrink the size needed for the input register of the algorithm down to n over 2 plus a negligible amount of qubits. This optimization doesn't affect at all the size of the output register. So once we've acknowledged it, the natural question remaining is what can be done about the size of the output register and is there a way to reduce it to? The answer is yes, and to do so, we are going to take inspiration from a theoretical idea that was presented by May and Schlipper in 2022 that comes from the following observation. Assume that you have a sequence of numbers that is periodic and a hash function. If you hash every number of your number sequence to obtain a second number sequence, the resulting number sequence will also be periodic, and moreover, if your hash function is chosen well enough, the period will be the same. Once we've observed that, we can think, we could run Shor's algorithm on a register that contains a superposition of the pairs x and a hash to the a to the power of x modulo big N instead of containing a to the power of x modulo big N itself. This should work the same, and if our hash function output holds on less qubits than the a to the power of x modulo big N we would have had instead, this would allow us to reduce the size we need for the output register of Shor's algorithm. This is exactly what we are going to do, and concretely, we are going to take, for a hash function, the hash function that sends an integer z to the first r bits of z, or to put it in another way, we send the integer z to z modulo 2 to the power of r. Which is very practical because now our output register is only r qubit long. But the problem with this, the challenge with this idea is how do we compute concretely a to the power of x modulo big N modulo 2 to the power of r? Because we can do this computation naively, okay? If we do this computation naively, we have at some point to compute a to the power of x modulo big N on our quantum computer, and we still have to store it, and we still need roughly n qubits to do that, which is precisely what we want to avoid. Please note that this difficulty right here is one of the big reasons why the idea of May and Schlipper was sketched theoretically, and they didn't provide a concrete way to achieve this kind of computation, so we are filling that gap technically. So in order to obtain the value that we are interested in here, we are going to need to use a number of arithmetical and computational tricks that I'm going to present. The first one is actually not specific to our memory optimization at all. So the first trick, let's start from the naive computation sequence we would normally have, and let's see if we can improve from it. The first trick we are going to use to compute a to the power of x modulo big N modulo 2 to the power of r is we are going to decompose the exponent x in a binary mode. So the x0, x1, etc. are all 0 or 1. If we do that, you see that you can rewrite the a to the power of x as a product of some specific integers a to the power of 2 to the power of I to the power of 0 or 1, depending on the value of xi. This is interesting for us because let's assume that you set a to the power of I parentheses to be the smallest positive integer that is equal to a to the power of 2 to the power of I modulo big N. In this case, you can also rewrite a to the power of x modulo big N as the product of the a to the power of I parenthesis to the power of xi, and then modulo big N. This is a consequence of the fact that you know a modulo n times b modulo n is equal to a times b modulo n, basically. This is also interesting for us for the following reasons. By definitions, the a to the power of I parentheses are at most n bit long, okay? Which means that this integer y right here is at most n square bit long, okay? So now our computation sequence has changed again, and we want to compute the integer y that I just presented, and then modulo big N, and then modulo 2 to the power of r. To do that, the general strategy is going to be the following. First, we are going to, well, concretely compute y by computing the value of y modulo a set of several distinct, very small prime number p. And we are going to retrieve y modulo the product of those prime number p using the Chinese remainder theorem. And with luck, or with careful setting, more accurately, we will be able to know if y is equal to y modulo the product of those prime number p or not. This kind of computational trick is called is a combination of the residue number system and the Chinese remainder theorem. Once we will have computed y, we will need to compute a modulo operation, which is something quite hard and costly to do on a quantum computer, typically because it's not a unitary operation, as you may know. So in order to compute y modulo big N, we are going to use a computational trick that's called the Barrett's reduction trick that I'm going to introduce later on. And then we just have to apply the modulo 2 to the power of r operation, which is basically a free operation to do since it's a bit truncation. So really, it's not hard to do. So as I just mentioned a few slides ago, we know that y is at most n square bit long. So we are going to assume that we have an integer m that is a product of several small prime numbers, p1, p2, etc., distinct prime numbers, that is always bigger than 2 to the power of n squared. So m is always bigger than y in any cases. Because of the structure of M, we know that we have the ring isomorphism that is written right here. And because of that and the Chinese remainder theorem, we know that we can write y modulo big M as a sum over the prime factor of big M of y modulo pi times some cofactor that depends on the said theorem. Also, because we know that M is always bigger than y, we know that y modulo big M is equal to y. So this gives us a way to compute the integer y we're interested in. And this is especially practical for us for the two following reasons. First, the factors in front of the y modulo pi appearing in this sum are very well known, and we can pre-compute all of them, so we don't have to compute or deal with them on a quantum computer. The second reason is that the y modulo pi, okay, as you can see, we can choose the pi to be to have a bit size of log n, where n is the bit size of the integer big N we want to factor, so we can choose them very small. So the y modulo pi we have to compute y in the end are also very small, and basically we don't need a lot of qubits to store them. So that's the two main advantages of this way to compute y at this point. So let's note this integer right here, so the integer that corresponds to the sum over the p, prior to the modulo big M operation. Now again, our computation sequence has changed, and we want to compute z, and then y, which is equal to z modulo big M, and then modulo big N, and then modulo 2 to the power of r. We are starting to have a lot of modulo operations to compute at this point, so precisely the modulo big M and big N operations that are quite costly, as I mentioned earlier. So to do that, we are going to use Barrett's reduction trick that consists in the following. If you want to compute the integer part of, for example, z divided by big M, you can choose an integer u well enough in order to have, with a very high probability, the integer part of z divided by big M that is always equal to this integer part right here, which is practical because, once again, the integer part of 2 to the power of u divided by big N, we can pre-compute it, so we don't have to do that on our computer. And the integer part of an integer divided by a power of 2 is a bit shift, so it's extremely easy to do. This is useful for us because, as you can see, we can write z modulo big M as z minus this integer part we are trying to approximate times big M. And so now we have a very practical way to compute our modulo operation. And we are going to use it both for the modulo big M and modulo big N operation. So now, since we have two consecutive modulo operations to apply, we can rewrite a to the power of x modulo big M as this kind of addition and subtraction formula right here, with Qm and Qn being two quotient of Euclidean divisions defined right here. Now, I'm going to ask you to believe me on the formula I'm going to present to you right now, but because of all of the tricks I presented you, we can show that with integers u and u prime well chosen, we can express the different quantities we need to compute here, z, qm, and qm, as the following kind of formula right here. There is something, I mean, again, everything that is in gray is either something very easy to compute even on a quantum computer or something that we can't pre-compute in any case. There is something very interesting to notice on those three formulas is that all three of z, qm, and qn integers can be expressed as sum over the prime factors of big M of y modulo p times something. Which this is the reason why we can actually, for example, if we are working with the first prime factor of big M, we can compute y modulo p for this first prime factor and update those three quantities according to their formulas, and then we can reuse the same slot of qubits we just used to compute y modulo p, to compute the y modulo, the next prime factor of big M we have to deal with. Basically, what I'm trying to say is that because of the way those three quantities are expressed, we can compute the y modulo p recursively and use the same slot of qubits for all of them, which is a very important thing to note because if you remember, I said earlier that the prime factors of big M are roughly log n bit long, but there is also n square over log n of them. And so if we had to store every y modulo p on different slots of qubits for every different prime factor p, we would, in fact, we would have a memory complexity that would be worse than the memory complexity of the original Shor's algorithm. So that would be a huge problem. Let's do a quick performance recap. So I said earlier that with all of the tricks I just presented you, we are able to achieve a qubit count of n over 2 plus a negligible amount of qubits to factor or integer big N. This means that concretely, if you want to factor a 2048-bit long integer, for example, you will only need 1,730 qubits, which is even less than the size of the number. This isn't a free memory optimization. Unfortunately, it comes with an overhead in the gate count of our version of Shor's algorithm compared to the original one. But you can note that the depth isn't changed with this optimization. So that's something. Now, to sum up, what mainly allows the optimization I just presented you is, again, the residue number system and the Chinese remainder theorem that allows you to compute and deal with very large numbers without having to compute them straightforwardly. There is also the Barrett's reduction trick that is a huge help when you need to compute a modulo operation. And last but not least, the fact that you can compute the y modulo p successively and reversibly is also a huge foundation of this memory optimization. This is the end of this presentation. Thank you for your attention. And if you have questions, now is the time. And sorry for the technical issues.
Are there questions?
I was wondering if you think that it's possible to apply the same ideas to elliptic curve cryptography.
Oh, that's a great question. Thank you for asking. We tried extensively. The problem is that, you see, I mean, one of the main reasons this optimization works, I mean, the starting reason why this works is the residue number system, which, I mean, there isn't any equivalent with elliptic curves. I mean, the idea of computing a point modulo another point isn't something that technically it exists with isogenies, but it doesn't have the same properties than the residue number system has, and so it doesn't imply any size reduction in the coordinates of the point you are manipulating. So that's, yeah, basically, specifically the residue number system tool doesn't apply very well with elliptic curves, and that's a huge problem when you want to use this ID with elliptic curves. We didn't find any way to solve this problem for now, but if you have suggestions, I'm open to it because we are kind of stuck with this.
It seems like the division that happens, or the modular inversion, is the main issue.
The division that happens with the modular inversion.
When you implement a point addition, there's a modular inverse that happens.
Oh,
yeah. That doesn't follow the rules of residue arithmetic.
Yeah. Basically, that's very good intuition. Basically, what we thought about doing for elliptic curves at the beginning was that we wanted to compute the point addition projectively in order to avoid divisions and to do the division at the end after after the Chinese remainder theorem. The problem is that this doesn't work, basically. And so, yeah, doing the division within the residue number system is kind of a nightmare. Technically, it's doable, but basically it increases the size of the big M number we would need in a way that completely defeats the point of the memory optimization.
Great, thank you.
We probably have time for one more question. Yes.
Thank you. So if I understand it correctly, so the bottleneck of further reducing down the number of qubits is probably the input number compression?
So, sorry, I didn't quite catch that.
So you say like your algorithm works on like roughly n over 2 qubits, and I think that's consistent with the number of qubits needed to represent the input, right? Mm-hmm. So I don't see any constraint in your algorithm that or further reducing down the number of qubits. So I guess the bottleneck is in the input representation, right?
Yes, exactly. Basically, okay. Almost, but not exactly. Actually, there is two bottlenecks. If you remember, when I said we take the integer modulo 2 to the power of r, there was, for example, r is equal to 22. The tricks we use to reduce the size of the output register comes with some error in the computations we make. And if you want to have a nice trade-off between the amount of errors you introduce with your memory optimization and the execution time of the algorithm, you have a minimum value for the integer r you are choosing for your hash function. So that's the first thing. And yes, basically, the biggest, concretely, the biggest bottleneck for the reduction of the memory complexity is the input register, and it's linked to the Ekera Hastad method that you can look into if you want. Does that answer your question?
Yeah, sure.
Okay, cool.
Thank you.
Let's thank our speaker again. And everyone, please remain in this room for the conference photo.
Yeah, yeah.